Welcome to PLC Programming Module 1, Chapter 2. Thank you for sticking with this. If you like the content, please hit the like button and also subscribe to the channel. So let's get started on Chapter 2, Numbering Systems. Module 1, Chapter 2, Number Systems. Numbering systems are used to organize and manipulate memory locations. There are several systems in use in computers and PLC systems. Binary system. The binary system is used for singular bit representation. A bit is either on equal to 1 or off equal to 0. The binary system is called base 2. The bit location is represented as a power of 2. 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power, 4. Third power is 8. Fourth power, 16. Fifth power, 32. Sixth power, 64. And the seventh power, 128. The eighth power is 256, and so on. A bit can only be equal to 1 or 0. A computer adds the binary addition even if it's inorganized by a different system. Binary condition 0 plus binary condition 1 equals binary 1. So if you take binary 1 and you're going to add another binary 1 to it, it equals 1, 0, not 10. In binary, which in there is only one discrete location, when 1 is added, it shifts the bit to the left one location. The result is the second bit, 2 to the power of 1, equals 2. And notice 2 to the power of 0 is 0. So let's add one more. Binary 1, 0 plus binary 1 equals binary 1, 1, not 11. So if 1 is added, it loads the bit to the right with 1. The result is the second bit, 2 to the power of 1 equals 2. Notice 2 to the power of 0 is now a 1. The result is decimal 2 plus 1 equals 3, decimal. A byte is 8 bits, and 0 being a real location, the max decimal number a byte can be is 2 to the n minus 1, or 255. That is 2 to the power of 8 equals 256 minus 1 equals 255. The way you get there is if you took all the bit locations and their power decimal equivalent, 2 to the 0, 1, 2 to the 1, 2, 4, 8, 16, 32, 64, and 128, bits 0 to 7, you get 255. Binary coded data, or BCD. Binary coded data is a grouping of each digit's binary equivalent treated as individual nibbles, 4 bits. Even though the data appears to be connected, it is treated as groups of 4. This stems from older technologies of thumb wheels that would be used as HMI connections to set values in early PLC systems. Example, take a 4-digit thumb wheel set to 1509. Taking each digit in order right to left, 1, 5, 0, and 9 on the thumb wheel. These are the binary equivalents for each digit. Ones complement binary. The ones complement of a binary number is simply the inverse of each bit location. Take the binary original bit pattern of 010111110. Take the ones complement of it. You can see it's just the opposite. 2's complement binary, add 1 to the ones complement. So you take the original binary pattern, you take the ones complement, add 1, and that is the 2's complement value of the original bit pattern. Subtraction by addition. If you take the number 44 and you minus 13, you get 31. Let's do this in the binary format. 44 has this particular bit pattern. If you took the power of each of those digits and add them together, you would have the decimal equivalent of 44. Same thing for the number 13. You take 2's complement of the divisor, take the 1's complement of that, add 1, and you get your 2's complement. "44 is 243. The last bit carries out of the result. The result is 31. 2 to the 0 power is 1, 2, 4, 8, 16. Therefore, 1 plus 2 plus 4 plus 8 plus 16 equals 31. The numbers from 0 through 15 in decimal, binary, octal, and hexadecimal are formed here on this list. Octal, base 8, and hexadecimal, base 16, compared to binary, base 2, and decimal, base 10. The octal numbering system is called a base 8 number system. It uses the digits 0 to 7. There are no 8s or 9s. The next number after 7 is 10. The next number after 17 is 20, and so on. Hexadecimal numbering system, there are 16 hexadecimal digits, and they are from 0 to 9, and then the letters A through F represent the numbers 10 to 15. So a single hexadecimal digit, boy, say that 3 times fast, can show 16 different values instead of the normal 10. And the purpose of this course is not to teach hexadecimal or octal or binary. It's simply to show you the representations of how the PLC uses these systems. So let's look at example 1. What is 4B5 in hexadecimal? The 4 is in the 16 by 16 position, so that means 4 times 16 times 16. The B is 11. Is in the 16 position, so that means 11 times 16, and the 5 is in the 1 position, which means 5. So if you take that number 4B5 in hexadecimal and do the math, you get 1205 in decimal. Example 2. What is 2.3 in hexadecimal? On the left side is 2, and that's the whole number part. The 3 is in the 16th position, meaning 3/16. So 2.3 is 2 and 3/16 equals 2.1875 in decimal. I pulled this off of mathisfun.com, and I suggest if you don't understand hexadecimal or octal or even binary, there are multiple sources on the internet, in engineering forums, in Math is Fun, and other locations where you can go get a in-depth explanation of these numbering systems. The decimal numbering system is called base 10. It requires the numbers 0 to 9. A decimal point defines the fractional portion of the number. Your standard scientific calculator usually has conversion capability from one system to another. Chapter 2 is now complete. We're going to take a break. Thank you. We'll see you in the next chapter.